Here's where these exponent shortcuts really come in handy is when we're working with numbers in scientific notation, because in scientific notation, you're separating out the value of the number from the magnitude of that number. So what we want to do to kind of pick up on this pattern to see how this can be used as a shortcut is for each of these, just write each of the input factors or the numbers being divided in scientific notation, and then also write the product or the quotient in scientific notation. And you'll start noticing some patterns that emerge. So for example, just to show how this should look, this should be 2 times 10 to the 6th times 4 times 10 to the 4th power, and that equals 8 times 10 to the 10th power. Okay, so do that same kind of thing for each of the input and output values for each of these problems, and give them a look, and you should hopefully notice that there is a pattern that allows us to work with these really huge numbers, or in some cases really small numbers, in a way that actually a lot of times doesn't even require a calculator, or at least you could do mental math without using a calculator, because all of the numbers that you're dealing with, whether it's the bases, the exponents, or the values themselves, the non-exponential part of each number, they're all pretty easy to work with because of how small they are. And that's exactly what scientific notation and these exponent shortcuts do for us. So after doing that, go down here and you want to check your thinking. So hopefully what you notice is that you can multiply or divide or divide the values. Think of those as like the coefficients, the non-exponential piece of each number. Separately from their scale or their magnitude. And that's the base 10 part. The exponential piece of the number can be dealt with separately. So that's anything that's 10 to a power. And so it's these numbers here where you can use the multiplication or division shortcuts. Multiplying or dividing the actual values themselves is the same as any other numbers that you're multiplying or dividing. You can use a calculator if they're kind of messy, but sometimes remember, because those values are between 1 and 10, a lot of times you can actually do mental math with those, which is what makes this really cool. So to show what this looks like symbolically, you could look at some of those examples up there that you did, and you'll notice that this works, is if you have two numbers, so let's say you have a times 10 to the x, and you're multiplying it by b times 10 to the power of y, the resulting product could be written as a times b times 10 to the power of x plus y. So you're basically just using the associative property here, is you can take these two and multiply them separately from these two. And the same thing works for division. So if we did something like that and we did a times 10 to the power of x divided by b times 10 to the power of y, some other exponent, you can do a divided by b separately from 10 to the x over 10 to the y, which is why we can do our math this way. X minus y, that's that division shortcut. So try using these shortcuts on the examples shown, and sometimes I find it really helpful to sort of color code the things that I'm multiplying. A lot of times what I'll do is I'll say, okay, I'm going to multiply these two together, my values, separately from their magnitudes. I'm going to multiply those two together using that shortcut rule. So for example, 2 times 3 gives me 6, and then my power of 10 That's not just 2 ones times 3 ones, 6 ones. This is actually a couple of really large numbers. Then 10 to the 6th times 10 to the 3rd, 9 tens. So I write that as 10 to the 9th. Pretty easy for multiplying a couple of really huge numbers. Same thing goes for our division problems. So you can divide 4.8 by 1.2 separately from dividing 10 to the 7th by 10 to the 4th. 4.8 divided by 1.2 is 4. 10 to the 7th divided by 10 to the 4th is 10 to the 3rd. So I'm subtracting those. One thing to look out for if you made a mistake on any of these, one common mistake is remember your negative numbers. So this is a multiplication problem down here, third one down on the left side column. So that means you're going to be multiplying your values and then multiplying your base 10 numbers. And you're doing 10 to the 8th times 10 to the negative 5th. So you're going to be doing 8 plus negative 5. Remember, when you add a negative, you're effectively subtracting. The other thing to look for when you're doing these is shown on the bottom two problems. So something a little bit different happens on this one and this one at the bottom. So let me go over those a little bit more detail. So when you do your work on these, on the bottom left one, you're doing 5 times 3, which is 15. And you're doing 10 to the 5th times 10 to the 6th, which is 10 to the 11th power. Now that's equivalent, that is a correct thing to do, but technically it's not in scientific notation. In scientific notation, this first number shouldn't be 15 because that's greater than or equal to 10. It should be a 1.5. So what happens to our power of 10 when we do this? Well, what you're effectively doing is dividing 15 by 10. You're taking out another power of 10. It's there now. So 1.5 times 10 is 15, and then I still have my 10 to the 11th power, and I'm doing a little bit more simplifying. So this should be 1.5 times 10 to the 12th power. So it's like you're borrowing it, you're pulling out a power of 10 from that number that's too big and lumping it in with the rest of your tens. Something similar happens to this bottom right problem where you're doing division. Then you do 4 divided by 8, you get 0.5. 10 to the 7 divided by 10 to the 4th is 10 to the 3rd. So again, we have that problem of this being equivalent to the correct product of these two very large numbers, but it's not technically in scientific notation. So in scientific notation, this should be 5 times 10 to the power, because that first value should be 1 or greater, but less than 10. So it should just be a ones digit number. So what would be our power of 10 on there? In this case, instead of pulling a power of 10 out of that value and lumping it in with our powers of 10, this time we're actually pulling a power of 10 out of our 10 to the 3rd power. So you can think of this as being 0.5 times 10 to the 1 times 10 to the 2. So we still have all three powers of 10. It's just that I am using one of those powers of 10 to multiply it by 0.5 so that I now have not 0.5 but 5 ones. And so that means I'm left with 10 to the power of 2. So you're borrowing one of your 10s to increase the value of that first number.